Every year, China produces more than 2.1 billion tons of cement, the largest output the industrial world has ever seen. That ordinary-looking gray powder is the hidden backbone behind sea-crossing bridges, underground metro systems, and cities rising at a pace unmatched in modern history. But before it becomes the foundation for trillion-dollar projects, cement starts out as raw rock buried deep inside the mountains. Those rocks are shattered by industrial blasting, crushed under machines weighing hundreds of tons, heated to over 1,400 degrees, then shock-cooled to transform into clinker, the core material behind all concrete structures. Behind that transformation is a non-stop 24/7 operation, where every ton of rock is converted into one of the most essential building materials of the 21st century. And how China pulls this off, that's what you're about to see. The massive flow of cement produced each year brings in more than $200 billion, making it one of China's core economic engines. Its scale surpasses every major economy on Earth. In just 3 years, China used more cement than the United States did during the entire 20th century, a clear sign of an infrastructure boom that few nations can keep up with. Provincial expressways, a high-speed rail network stretching over 40,000 kilometers, and megacities like Shenzhen, Pudong, and Tianjin were all built in essentially a single generation, powered by this enormous cement industry. But that speed comes at a cost. Cement plants consume nearly 8% of China's total electricity each year, release more than 820 million tons of CO2, and generate massive amounts of fine dust that put heavy pressure on the environment. Even so, to maintain its status as an infrastructure superpower, China accepts these trade-offs, treating cement as the raw fuel behind its rapid national rise. The raw materials for China's entire cement industry begin in the limestone mountains that surround its heavy industrial zones. Limestone makes up 75–80% of the raw mix and provides almost all of the CaO, the key component that determines clinker formation. To keep transportation costs as low as possible, most plants are built right next to these quarries, turning extraction into the first link of a production chain that runs around the clock. On the quarry surface, geological engineers lay out a grid of drill holes, each 8 to 12 meters deep, aligned along specific directions to create a controlled break. The holes are filled with emulsion explosives, or ANFO, along with electric detonators and stemming materials to maximize the blast's efficiency. When warning sirens sound across the site, the blast sequence is triggered, ripping apart an entire bench and producing thousands of tons of fragmented rock exactly along the planned opening line. As the dust settles, large crawler excavators move in and load the rock onto 40–60-ton haul trucks or directly onto primary conveyors leading to the plant. Oversized boulders are broken down on the spot with hydraulic breakers to prevent blockages at the crusher. At the primary crushing station, jaw crushers or hammer crushers reduce the material further, bringing everything down to under 100 mm, the ideal size for blending and fine grinding later on. Alongside limestone, clay is also mined from nearby open-pit deposits using large bucket excavators. This area doesn't require blasting, but it still needs strict control over moisture content, chemical composition, and overall consistency, because even small variations in the feed can throw the entire clinker production line out of balance. After extraction, the raw materials move immediately into a large-scale transportation system where limestone and clay are carried non-stop through a fully mechanized, closed-loop route. At many modern plants, kilometer-long conveyor belts connect the quarry directly to the industrial complex, crossing hillsides, valleys, and technical corridors without a single intermediate stop. Thanks to this continuous operation, raw materials reach the preparation station at a steady, controlled rate, significantly reducing costs and minimizing bottlenecks at the primary crushing system. In more challenging terrain, heavy-duty dump trucks still play a supporting role, feeding additional material into the main transport line to ensure an uninterrupted supply for the production process. At the processing area, the raw materials move into the homogenization system, a crucial step to stabilize the chemical composition before fine grinding. From the main conveyor, limestone and clay are fed into the dome storage at a steady, controlled rate. Inside, a stacker spreads the material in thin, arched layers, forming a perfectly layered pile across the entire floor. On the opposite side, a reclaimer moves smoothly along the pile, recovering the material in the same order it was laid down. This layer-by-layer stacking and reclaiming method evens out variations between quarry batches and ensures a consistent, uniform feed for the production line. The blending process begins as each homogenized raw material is pulled into the automated dosing system, where belt scales continuously measure and adjust the proportions according to the plant's design formula. Once the mix meets the required ratios, it is sent directly to the grinding unit, the most energy-intensive stage of the entire line, and the step that ultimately determines the quality of the raw meal before it enters the preheater tower. Depending on the plant's technology, the material is fed into either a vertical roller mill or a multi-compartment ball mill, massive machines capable of continuous operation and handling anywhere from 100 to 500 tons per hour. Inside the grinding chamber, the intense compressive forces and friction from the rollers or steel balls break the material down to particles smaller than 90 microns, producing raw meal with a high level of uniformity. Some older production lines still use the wet grinding method, adding water to create a slurry. This approach makes chemical control easier, but consumes significantly more energy, so it is gradually being phased out in favor of more efficient dry grinding systems. Throughout the entire process, all operating parameters, including feed ratios, grinding speed, fineness, and gas temperature, are monitored in real time by the SCADA system to ensure the raw meal remains stable and consistent before moving on to the next stage. Heat from the hot gas flow spreads through the preheater tower, but the raw material must follow its own path before entering the harshest stage, the rotary kiln. From the top of the tower, the limestone clay mix drops through tall cyclone chambers, spiraling with the rising hot air. Each cyclone works like a natural heater, raising the temperature of every particle to around 850 degrees Celsius within seconds. In the calciner, the heart of the tower, carbonates break down almost completely, turning the raw meal into minerals ready for high-temperature reactions. This multi-stage structure operates like a vertical river of material, weaving through steel chambers and absorbing energy from the burners below. Coal was once the main fuel, but to cut costs and emissions, many modern plants now add alternative fuels. Shredded rubber from old tires, cleaned of metal and ground into chips, is injected into the burner, burning fiercely at nearly 1,000 miles and providing similar energy to coal with far less CO2. The entire process is tightly controlled by automation. Material drop rate, airflow pressure, and cyclone temperature are all kept at optimal levels to prevent over- or underheating. Even though the material moves quickly, every step aims for two goals: delivering a consistent feed to the kiln and reducing environmental impact. It's how China's cement plants balance massive output with growing pressure to green the industry, a clear sign of the country's infrastructure ambitions. The deep rumble of the rotary kiln mixes with the glow of the red-hot flame, creating a steady industrial rhythm. Inside the long steel tube, raw meal from the preheater drops in and slowly slides along the refractory lining, turning with the slight tilt of the kiln. As it moves into the hottest zone, each grain of limestone and clay is exposed to more than 1,100 degrees, where their original structure begins to break down and reorganize into new minerals. At this temperature, CaCO3 rapidly decomposes, releasing CO2 and forming highly reactive CaO. The CaO then combines with silicates and aluminates in the mix to produce the key clinker phases: elite for early strength, belite for long-term strength, and illuminate for setting behavior. This is the most critical stage of the entire process, where even small fluctuations in temperature or retention time can cause underburned or overburned clinker. To keep conditions stable, the control system constantly monitors kiln speed, fuel flow, and gas pressure using heat sensors and infrared cameras. The burners inject fuel in a swirling pattern, creating a long, penetrating flame that transfers heat deep into the material bed. Hot gases from the decomposition reaction are drawn out at the kiln inlet, carrying most of the CO2, while excess heat is recovered and sent back to the preheater. Along the kiln, the material gradually fuses into glowing red clinker nodules, rolling steadily along the kiln axis in the constant roar of fire and steel. The red-hot glow still clings to each clinker as they slide out of the rotary kiln, their constant movement carrying them straight into the cooling system. On the moving grate, powerful blasts of cold air are pushed upward from below, taming the intense heat that's still well over 1,200 degrees. Each clinker slowly changes color as it cools, sending waves of heat rising in steady pulses. The haze of warm air mixes with the fading red light, creating a vivid scene where heat and mechanical motion blend together in the process of stabilizing the clinker's mineral structure. The residual heat from the cooling process still clings to each clinker as they slide into the high-capacity grinding mill, processing several hundred tons per day. Here, the clinker mixes with about 3 or 5% gypsum and mineral additives, such as fly ash or ground granulated blast furnace slag. Under continuous pressure and friction from steel balls or rotating rollers, the mixture gradually breaks down into fine cement powder with a fineness of around 4,500 cm. Fine dust rises into the air, and the reflected light on the machinery creates a scene that feels both mechanical and alive. Automated dosing systems and sensors monitor every batch, ensuring consistent mineral composition, fineness, and strength, transforming the solid clinker into the refined foundation of high-quality cement. The fine cement powder drops into the intermediate silo, flowing with a steady rhythm like a small river inside the plant. An automatic sampling system extracts a portion of the powder and sends it to the laboratory, where advanced sensors and analyzers record key parameters: fineness, moisture, mineral composition, and strength development. Each value is continuously compared with internal standards and national specifications, ensuring every batch leaving the plant remains completely uniform and stable, a place where mechanics and precision meet in a seamless, almost living rhythm. The uniform cement powder flows from the silo into the packing area, where the rhythm of the plant is defined by a continuous stream of material. Each empty bag is positioned under the filling nozzle, and precisely 50 kilograms of cement drop in, thanks to a modern dosing and weighing system. The automatic packing line runs smoothly, producing 500-600 bags per hour, creating a scene that feels both mechanical and alive. The sound of falling powder blending with the reflections of light on the metal surfaces. At advanced plants, robots fully replace manual labor, guiding bags into place, filling them, sealing them with heat or tight stitching, and ensuring accuracy in both weight and closure. The filled bags move down the conveyor, where sensors monitor each one, removing any that fall outside the required specifications. Next, robotic arms stack the bags onto pallets with brick-like precision, 40 bags per pallet. As the load is shrink-wrapped, the warehouse lights reflect off the surface of each bag, forming a refined industrial scene where machinery, automation, and precision move in perfect harmony, completing the final step before the product leaves the factory. As it leaves the automated warehouse, the cement is transported to concrete batching plants, where it joins its familiar companions: fine sand, crushed stone, and clean water. Automated dosing and mixing systems adjust every percentage with precision, ensuring each batch of concrete reaches perfect uniformity. Within minutes, the seemingly simple gray mixture becomes a foundational material ready to support massive structures. From river-spanning bridges stretching thousands of meters to skyscrapers and expressways worth billions of yuan, every concrete element carries the imprint of advanced engineering, automation, and strict quality control. The sounds of mixers, conveyors, and concrete trucks blend with the rotation of tower cranes, creating a rhythmic industrial symphony. Every grain of sand and every piece of aggregate is monitored for weight and size. Even roller vibrations and slight temperature changes are recorded to guarantee structural stability for centuries. In this vast landscape, concrete is more than just a material. It is a symbol of technical strength and modern infrastructure, present across China's trillion yuan megaprojects, where technology and labor come together to build greatness. From these refined materials, cement becomes a solid foundation behind modern, massive structures. Every bag of cement and every batch of concrete carries precision, technology, and mechanical rhythm, contributing to the construction of bridges, highways, skyscrapers, and trillion yuan projects across China. This process is not just a story about materials, it's a testament to the blend of labor, engineering, and automation, where quality and performance are carefully controlled at every step. If you found this journey fascinating, be sure to like and follow Mandarin Tech to explore more engineering and infrastructure wonders from around the world.